BKW Physics. I'm Mr. McConley, I don't know my own name. Today we're going to talk about variables that affect resistance. And the four that I've listed are the type of material, the length of the conductor, the cross-sectional area, and the temperature. So let's go through each one. First of all, basically most people know that metals are good conductors. But a lot of people don't know why they're good conductors. And the idea here that you have to know is that metals have a lot of free electrons. And if you have free electrons, that will allow for the flow of current to go through that material. Now, there are other non-metals that conduct, but basically you got to know that things like aluminum, copper, those are good conductors. Things like wood, plastic are really totally the opposite, and in fact we call them insulators. So the type of material that you're talking about will definitely be one thing that affects resistance. And there's a chart in your reference table, if you can pull that out real quick. There's a chart in your reference table on the section by electricity and circuit symbols, I guess page 4. And it says resistivities at 20 degrees. And we'll get to the temperature in a minute. But resistivities. And it lists aluminum, copper, gold, nichrome, silver, and tungsten. And it shows you that these different metals have different resistivities. Now when we talk about resistivity, that's the idea of resistance to electron flow. And so the number that is the lowest number is the one that's the best conductor. So if you look at this chart, just real quickly, which one has the lowest number? Lowest number. Joe? Lowest number.
Silver.
Silver. You can see that silver is going to be the best conductor. So why don't we wire our houses with silver? Well, I think you can obviously realize that that would be really expensive. Silver is not cheap enough to run your wires in your house with. However, a lot of times with automobiles and you know, in computers where the connection is really important, they might put a little bit of silver there to make the connection better. One thing I want you to notice is that nichrome says 150 E8, negative 8 actually. That is bad scientific notation, but I think they wanted to write all of them so they were negative 8. And if you think about it, 150 E negative 8 is a much larger number. So nichrome is a terrible conductor of electricity in comparison to the other ones listed. Copper and aluminum are the two that we use for electrical wires in houses because they're readily available, they're malleable, you can bend them, and they're fairly inexpensive. Alright? And gold's not as good as you think. But gold has the advantage that it doesn't corrode. So sometimes gold is a good conductor because of the fact of it that it won't corrode. Moving on. The other thing you got to consider is the length of the conductor. I always think of it this way, or I always give this example. If you wanted, out here in the country, you might want some Christmas lights down in your mailbox. Fine. So you run an electric cord out and you put some Christmas lights and you plug it in and it works, right? Well, what if you have a long driveway like me? My driveway's, 600 feet. So could I just connect one extension cord to the next extension cord to the next extension cord to get to the end of my driveway and have it work? Well, you could, but it might not even work if you put enough extension cords together because there's so much loss of electricity through the wire that by the time you got out there, the lights might not even turn on even though they're plugged in. Because the longer the conductor, you get more resistance. So if it's a longer conductor, you're going to get more resistance. So how do you combat this? Which actually is the next category. If you got to run a wire a really long distance, the wire needs to be very large. Cross-sectional area means when you're looking at the end of the wire, how big is it? So if you need to run a wire way down your driveway 600 feet, you can't run a skinny little extension cord wire. You have to run a pretty big wire. Because if the cross-sectional area is larger, you get less resistance. So as the wire becomes fatter, larger, you get less resistance. And a lot of you that are into music, you know that, because when you run speaker wires, and you want them to be quality, you run larger gauge wires, correct, Chase? Yes? So, the last thing is temperature. Temperature. When metals get hot, you get more resistance. However, when nonmetals get hot, you get less resistance. And this has a lot to do with the confusion with computers, because you know, certain parts of the computers like to stay cool, and other parts of the computers actually work better when they're warmer. So that's because of the metals and the non-metals parts in computers. But basically, back to the reference table, all the resistivities that are listed there are at 20 degrees Celsius. So we try to hold the temperature as a constant in most of the physics problems that you'll work on. Now the equation. There's actually a great equation that's found on the same page of the reference table. It's up near the top, and it is the resistance of a material is rho L over A. R is resistance, and resistance is listed in units of ohms, just like we talked about the terrible ohm symbol. Let me try again. There. Resistance is in ohms. That funny rho is actually the resistivity. So you can find that resistivity. And you can find that on the chart on the same page. And resistivity is in ohms times meters as units. L is the length of the conductor. That's going to be in meters. And A is the cross-sectional area that we just talked about, and area is always in meters squared. So this is a handy equation, and it's not at all hard to use, because basically, I would say you have an aluminum conductor that is a certain length and has a certain cross-sectional area. You would be like, oh, there's the length, there's the cross-sectional area. You'd look up the resistivity of aluminum, 2.82 E negative 8. You'd plug them in, boom, you'd have the resistance of that particular conductor. It's quite easy to use the equation. All right, so that's variables that affect resistance and an equation that ties them together. One other thing I'd like to do, though, is to point out that previously we used the equation power is current times voltage. And what I want to expand upon that is to tie in also our newer equation, resistance being voltage over current, Ohm's law that we talked about yesterday. And I want to tie the two in. Like, what if I rearranged, so V equals IR, and then I plug it in right here? Well, I would get power is I times R, or I squared R. And that would be a new reference table equation. Remember, these are also reference table equations. And in fact, I could rearrange again and rearrange for I. So I could say I is V over R and plug it in here. So I could get power is V over R times V, which would be V squared over R. Another reference table equation. Now, I don't want to belabor this, because the fact is, I'm just taking the equations and I'm combining them in different ways. And on the reference table, you will find that they write it all out for you. They write it this way. They write P, kind of write it the exact same order. P is VI. It's also equal to I squared R. And it's also equal to V squared over R. And they write this on one line, just like that. So they're trying to tell you, if you have V, I, or R, or at least two of them, if you have two of the V, I, or R combination, you can always get the power. And remember, power is in watts. Okay? So that's a handy-dandy thing, and I'm just trying to give you some context as to how they came up with it. Similarly, on the next line, same idea. We know that work is power times time. We did that ages ago. But now that you're talking about electricity, look at all the different ways you can write power. So, you can write power as I times V, and then tack on the T. You can write power as I squared R, and tack on the T. Or you can write it as V squared R, and tack on the T. So basically, what they've done in the next line on your reference table, I'll clean it up a little bit here for you. On your reference table, they wrote work is power times time. They also next wrote is V times I times time. I squared R in T. And finally, V squared times T over R. And they write that all combined for you, so you're realizing that you can use any of those. As long as you have these variables, you can get the work. So, I just wanted to point that out. I didn't want to spend a lot of time on it, but the fact is, they show you that you can get power in a multitude of different ways and work also for the electrical chapter. So for today, physics.